Okay, it's okay.
Okay, so I guess I will take it today because Mateus is hiccuping a little. So, okay, welcome to our next Quarkus book club today about chapter 8, which is named Reactive Programming. I will share my screen and we can dive right in. But I cannot share, Mateus. You need to make me a co host.
Okay. Now you can share.
Now I can share. You are correct. So now you should see yourself and now you should see the book. So this is one of the shortest chapters, but it's coincidentally one of my favorite topics to talk about because I really believe that reactive programming is a basically very great way to write programs, even if many people will disagree with this statement. But I really think that every Java developer should actually understand what reactive programming is and to consider when or if to use it in their applications. Before we dive in, I just want to really mention because today is actually like one of the rarest event of the year. Yeah, I don't know how many of you are like actually curious in astronomy, but today is actually the biggest or largest and the brightest moon of the year 2025. So if you will have some time after the talk, then you should go and check the moon because it's really beautiful. And now let's dive back into reactive programming because in the book we have everything on like figures on images. However, I am also doing a talk about Project Loom. I decided that today we will actually look to my slides because I want to make it dynamic because like if it's like a static image it's not so interactive. So I will show you slides from my talk which is called Is it Loom really the future of enterprise Java? But it doesn't matter. I just want to start that if you didn't know that Quarkus already has more than 1,000 contributors, like in less than 6 years, that's quite an awesome feature. Here we have all of them. But where I want to get is this traditional processing. So when we basically write programs nowadays, or like in normal imperative paradigm, imperative way of writing the code, you basically execute the statements one after another. So if you, for instance, make here we are using REST client, which we had already in chapter 4, to make an outgoing HTTP request. Basically, after we call this blocking get, we are blocking the thread which is executing this call method until this HTTP call returns a response, which is then parsed by Quarkus into a string, which we are requesting here, and then we are continuing with our program. So how that would look like in an image. So here we have our Quarkus application server, and here is the remote service that we are calling with that HTTP call. So when the request to our application comes to our application, we will allocate some platform thread, so real operating system thread, which is in Java called platform thread, which will execute our HTTP get, from the start to finish. This is everything handled by this single thread. Usually, how all of Java frameworks do this, they are usually keeping some pool of these threads, and basically, after the HTTP request is done, then it's returned to the pool, and another request can take in. But let's focus now on that single request. So when the somebody calls our HTTP GET, we will start executing our method until we will get to that remote call to our remote service. So when we will make this remote request RR1, then basically we are waiting for the period until that execution is done on the remote service, until we will get remote request response, I guess, back. But for the duration, the thread, that platform thread, which is executing our request, is blocked. Until after we will basically get the response, we can continue with whatever we had there, I don't know, uppercase or something like this. If we will get another request in the meantime, as I mentioned, we will take a new thread from that pool and we will start executing exactly same thing on a new request. When we will get a further request and this will come after, let's say, this first request 1, the red one, is already finished. We can reuse that same thread and basically continue with the execution. But as you can see, for the duration of the request, basically nobody can use these operating system threads here, here, and here. Okay, so, and this continues forever. So what is reactive programming in nutshell is writing your programs in a way which is working with something which is called continuations or promises. You can, maybe you know it from different languages. Basically, you will define what should happen after your asynchronous response is gotten back from the remote call, in my case, but this can be any asynchronous operation with this kind of it's called reactive API, but it's basically just really usually some invocation on the result. So you don't really have the result already computed. You are just saying what should happen after the result is received. But as you can see, this is like very close or very similar to what we had before, because we are just like mapping whatever string will come back from this reactive get to uppercase before we will return it. And notice here that we are already returning something which is called unit, which is one of the, you see, Mateus, now I am hiccuping. This unit is coming from a project called Smora Mutiny. We already saw it before, but we will get to that later. So for now, I will park this. I just really want to show the same image as soon as possible because this is the best explanation, I think. So again, we have our server and we have the remote service, but this time we have a special thread, which is still an operating system thread, but it's assigned as an event loop, which is a concept I think originally taken from Node, but in Quarkus this is adopted through Vertex framework, which is a special thread, which is used to basically execute asynchronous code. And there is one single rule: nobody can ever block this thread. So any blocking operation on this thread is not allowed, and actually Quarkus will shout if you will try to block this thread. So how will the execution now happen? Usually you have very small number of these event loop threads in your application. I think that by default it's a number of threads or maybe half of number of threads on the machine. So basically, when we will get a request now, we will start executing it on event loop if it's free. But when we will get to that remote request part, which is now written in a reactive way, we will basically park that somewhere else. We are not blocking the event loop thread. We are basically just define that continuation somewhere in memory. This is handled everything by Mutiny in the background. And basically, we are done for now. So if there is a second request coming to our application, we can start executing it right on the same thread because it's now free. Nobody is really just like idly waiting on this thread. Again, when we will get to the second remote request, we will just move it somewhere else. If then we will get a response back from the first request, we will just basically start executing that continuation which we had parked somewhere else on the same thread like this. So as you can see already, we are just utilizing single thread better. If we will get the second response back, then exactly the same thing. If we have a request free, we can again start executing it on any free event loop thread. And if we are moving somewhere else and there is nothing, like no other work to be executed on event loop thread, then it can be idle. But basically, you already see the benefit. I think that this is the last message, which the reactive programming will give you, or the asynchronous way of programming will give you. It will give you more performance, more throughput, just by better utilization of your existing resources. Because you can imagine that, like, if you scale this to thousands of requests and they can interleave with each other on a very small number of event loop threads, or even if you make, like, because I think this is configurable, you can define multiple event loop threads. They will just use the available CPU better, like more of the time than the blocking way, because the blocking way will just really block the thread. So it's idly waiting, not doing anything useful. But that there is this like single rule that you should never block the event loop thread, because then bad thing will happen, and we will get to virtual threads later. So now we will go back to the book. And again, if you have any questions, just shout, because I am on a single screen, so I don't see the chat or if somebody is trying to speak. So here we have exactly the same images, just more statically, because like in the book it's not so interactive. But I want to show you this part. So as I mentioned, in normal imperative programming, basically when we write any blocking operations, and that can be remote calls, databases, like any, I have no idea, like nothing comes to mind, like messaging, for instance, with Kafka or something like that. Uh, Basically, if such an operations or remote code is like started or it's sent through the network or to the database, you typically in every normal way of like normal Java framework, you will just idly wait until the result is computed, because your program cannot continue until you have the result. That's exactly what we had in that statement. We need that string response back before we can execute something on it. So we need to actually wait for it to happen. So you see that this time is really just wasted, because somebody else might want to use this thread in this meantime, but they cannot. With the reactive programming, you will define that continuation, which is basically just really a pipeline or like a set of operations that will execute on top of computed asynchronous result. So it's like basically a definition what should happen when the operation will end or you have the result. So you see, it's like a little bit like off, like around itself, because you are first defining what should happen, which is normally coming after it happens. But when you write it like this, then basically nobody cares what will happen after the operation ends, because you already have it defined when the operation starts. So this is how basically you need to think about, oh, that's too much. You need to think about how the operation is handled. In your code, I think that I have examples somewhere here, so I will jump around a bit, but yeah, let me go by the book. So basically that would be like how we are like basically thinking about reactive programming. But you need to like you probably already see that like this way of like chaining of continuations can become problematic, because then you are you cannot really rely on the stack traces, because then a lot of things are happening in the background which you don't see. But in general, from your perspective, from a user perspective, this is extremely simplified, because Quarkus will give you something which is called small rime mutiny. This project is basically very heavily integrated directly in Quarkus core. So we already saw it with gRPC, for instance, in chapter 4, because sometimes it just doesn't really make sense to push blocking APIs, even if it's possible to implement it with blocking APIs. But reactive APIs fit way better. And that was exactly our case with chapter 4, when we were implementing the gRPC streaming, because streaming is actually a continuous flow of items, and you need to perform some operation on that. So like it directly maps to a continuous stream of items, which we have directly typed for in small rime mutiny. So before I will explain what mutiny is, I want to really shortly touch on reactive streams, because if you are not familiar with the specification, which you can find on this URL, it is basically really a non-blocking asynchronous API in Java. It was first started as a separate project, but since JDK 9, this is already integrated into JDK, into this Java util concurrent flow class, where you have these 4 subclasses. publisher, which is publishing items, subscriber, which is consuming items, subscription, which represents the actual connection between publisher and a subscriber, and a processor, which is some intermediary, which is also a publisher and also a subscriber. So it's probably from the other side, it's subscribing to some stream coming from one side and publishing to some stream on the other side. How that looks like in an image, or because I don't have this in the slides, how these like interactions between publisher and subscriber looks like when you are dynamically providing it. So you have some implementation of the publisher and some of the subscriber. The first like link initiation is coming from the subscriber, which needs to subscribe to some publisher, to some stream of items. This can be like any number of items because you don't really know what publisher will be publishing, or if the publisher will even publish something or not, because like you cannot know this, or it can be potentially like infinite number of items. So when you are subscribing to a publisher, you will call subscribe method on the publisher, passing you basically the instance of the subscriber. Publisher on turn then calls on the subscriber on subscribe callback, passing the subscription object. So that's one of that 4 classes from the flow class, which the subscriber then uses to request items to be published by the publisher. This as that request with this number is a concept which we call back pressure, which is basically ability to control the rate of publishing of items from the publisher from the subscriber side. So if the subscriber is not keeping up with the rate of published items, they can just say request only 1 or request 10 if I'm like having a lot of resources and I'm processing everything extremely fast. So this is the back pressure concept, which is integrated into this whole reactive API, reactive streams API. So when the subscriber calls on the subscription request a few items, like in my case 2, then publisher is mandated to call on the next callback on the subscriber, basically n times. So in my case 2 times, it will basically invoke on next with the next 2 items published by the publisher. Then after these 2 are processed, then subscriber again can request more items and exactly the same thing will happen. Then if the subscriber will again request some items, and we will produce only 1 because we run out of items, then every stream can be, because it can be infinite, but it is completed by one of the on complete when it's success, or on error, passing the exception, or droppable. I think that I heard something. No, maybe not. So it's finished by either on complete callback on subscriber when there was no error, or on error callback when there was error. And then subscriber knows that the publisher published all of its items, and basically the whole interaction is finished. Yeah, it's basically written here. So how will I zoom out? Okay, so if we will basically take this concept into like real world application, like I told you, it's only 4 interfaces which you can implement. They don't have that much methods. However, this turns out it's not so easy to implement correctly. There is actually a TCK, which stands for Technology Compatibility Kit, for these reactive stream APIs to catch all the edge cases which can happen if this whole interaction will go wrong. And to implement this is extremely hard. So it's generally not recommended that you will go ahead and implement your own publishers and subscribers. However, nobody is stopping you if you want to. And actually, Mutiny will allow you to pass your own publishers and your own subscribers if you want to. So it's like fully like integrated. But this is what exactly Mutiny is. Mutiny is an implementation of the reactive streams APIs. So we have like publishers, we have also subscribers, which you don't usually see. that like that publishers are more complex, because or like more important, not complex, because basically from your user perspective, you are usually interacting just with two classes, uni and multi. Uni is a single asynchronous result or a failure. Multi is basically everything else. So it's potentially unbounded stream of produced items, and yeah, it can be infinite. So if you have a single result, uni. If you have multi, then potentially unbounded number of items. One thing that you can run into, and I saw that people are having issues like putting it together. Both of these times are, of course, parameterized by the actual type of the item which is being produced. So these are two are basically publishers. So Uni can also produce collections. So if you have like a Uni list of string, then it's not like that each item in the list is produced by Uni. Uni is always producing only a single item, which is a list. And we will, I think, see this later. So more or less, these two classes are having a bunch of static methods, which I will show you in a minute. Just I didn't generate the project yet, so we will get there in a minute. Well, let's do this. Why should I talk when I can write the code? So let's create Mutiny example. Don't worry about this because I'm running JDK 25. So yeah, like my SDK man is complaining. I need to look into it in some while. So actually, because as I told you, Mutiny is very heavily integrated in Quarkus. Go into presentation mode, please. Thank you. I don't need to add any extension because it's already included in every Quarkus application that you are writing. So if I take my greeting resource, I can directly start writing here uni, come on, or multi, if I can type multi. So you see, you have it already in your application. So what this uni will give you, you see, it's a bunch of static methods which you can directly use to create these asynchronous publishers. The easiest way is this create from item hello, and this is already a reactive item which is not ever going to be produced. I wonder, idea is clever enough to tell you this because uh, basically, as I told you, this will create a publisher, which is also like telling you in this error. Value is never used as publisher. Uh, Basically, by design, Mutiny and the whole reactive streams are lazy. So if nobody subscribes to a publisher, the item is never produced. So if you will not manually call subscribe here, as which you can see, you can subscribe with manual something like subscriber, very simplified UI, but usually you are not doing this manually. This item will not be produced. Oh, you know
Martin,
what? Yeah, go ahead.
sorry for interrupting you. We have
Okay.
a question, the chat from Mussolini. It's a long question, but okay. My question is about the reactive pipelines you are describing, like in figure 8.5 in the book. When building a long
Oh,
pipeline,
we will get to 8.5. I am still not there.
mm,
So probably
okay,
let's just park it. And if this will be still relevant, I don't know who asked. Then please, like, tell me. I will respond it. But we are still not here. I am
okay,
still just up here.
no problem. Then I will ask after.
Okay, we will
Perfect.
get there in a minute.
Okay, great.
So just to finish this, like you see that because I subscribe with that system out print line, we are actually invoking our unit. So this is done actually asynchronously, but you don't see it like this. What you will usually do is you will pass this uni, which you will create in some way, back to Quarkus. So I can return it, for instance, from my Jaxares method. like this. And if I call my method, I will get hello from reactive. So you will see that basically I am not subscribing to that produce publisher manually. I am returning it back to Quarkus, in my case, Quarkus REST extension. And Quarkus REST extension will actually handle the subscription when the actual HTTP response is or HTTP request in my case is passed from my command line. So this is how you will typically uh, interact with small RAM mutiny. You will either start with uni or multi dot, and then you will do something. So if I now I will probably hate myself because like I haven't done this in a while. So let's do it for fun. So if I would, for instance, want to create that infinite number of item or infinite stream, you can see that I have this create from create by, so I can like manually create from items, just 2 items, which will be produced by my stream, and return it back from my JAX-RS method. So if I now call my hello, yeah, it will produce both items. I was actually wondering what will happen. But if I do, I think here, no, like this. Oh, oh, oh yeah. Not to explain, but servers and events. Yeah, so this is what I wanted to do. So I changed the media type which is produced, which was originally just explained. So the whole item was just produced at the same time to servers and events, which is basically an HTTP type text event stream, which will stream your items one by one as they are produced by the server. Uh, so if I have only 2 items, you don't really see it, but I want to show you this infinite stream. So I can say create by instead of this and just say, oh no, it will be create from, it will be create from, uh, no,
Tiki.
yeah, it
I
was
think Tiki. Tiki.
ticks.
Tiki.
Yes, this is what I was looking for. Thank you, Mateus. So basically, I will create it from basically a tick every second, which will by default, I think, only. Oh, error. What is the error? Oh, so it's long. Okay. So I will just like very manually map this to hello plus x plus number because like why not? So now you will see that I'm already producing item every second and this would go forever. If I will not stop consuming them because my consumer is now actually initiated but my HTTP request, which is asking for servers and intents from my terminal. This minus stream, if you are not familiar with it, it's nothing fancy. It's just in HTTP a way how to pass the accept header, which I don't remember what exactly it is, but you can look it up later. So here we are already now crossing to that way to actually defining the pipelines because we are actually already defining some continuation that should happen every time an item is produced by this publisher. So if I would want to transfer it to something else, I can map it to something like next to uppercase. So now we are getting item produced like with uppercase. I don't know, I can filter every s ends with let's say 3. So now I should produce only items which are ending on 3. So now if we wait 13 seconds, I hope to get another item. Yes, so at least I can drink. So you already see that this would go forever, and this is the way how we will define this callbacks. So now the correct question, what is actually happening in the background when we will define that chain of continuations. That chain of continuations, you don't really see it here, but basically what this map function is, and you have a bunch of these methods on this. Usually I don't remember this Mutiny API at all. Like all of my programming starts with multi dot something dot and then auto completion until I will find what I need. It's quite hard to remember all the possible operations because you can see that this is a lot that you can choose from. What did I do? Yeah. So basically, each of these basically lines is already defining some intermediate processor from that flow or reactive streams API. Because what this is actually doing, it will take subscribe to an item produced by my Tix publisher, and it will produce a new item down the stream, which is changed by prepending hello space to it. Then I have another processor which will take again whatever is produced by this publisher and it will put it to uppercase. Then I have another processor which is basically taking again any item produced by the last publisher, and it will produce the item only if it ends with free. So it's basically not producing as many items as all of these producers or these free producers. It produces only every 10th item. If we will put this into an image, we have it here. So time is passing from top to down, and you see that we have our first publisher, which will invoke on item, which is that callback defined on the subscriber on the first processor. It will do its thing, and it will invoke on item on the next processor in the chain. And this is how that item is transformed and passed down the chain of the callbacks until you will reach the final subscriber, which in my case is, of course, my terminal. Uh, and if you have another item produced by the first publisher, so here we have our ticks, you see that each item will be basically passed every time through the whole callback chain, through all of the processors until it will reach the end subscriber. So this is how it's always coming down until you will reach that on completion or on error callback, which will then be passed basically exactly the same way. Now I would ask for that question. If you can tell me, Mateus.
Okay. My question is about the reactive pipelines you are describing in figure 8.5. Okay. When building a long pipeline with mult or uni, what is the most common gotcha or mistake a developer makes in a real-world Quarkus application? For example, we need to call a small blocking piece of code inside a transform stage, what is the correct way to do that without blocking the event loop? If you want to read the comment, it's a very long comment
No,
question.
that's actually a very good question.
Okay,
So basically, you are already going to slightly like further that I wanted to. So let me just copy paste. Oops, the example from the book. I will do another get. Let's call it book. I think it's producing string. I don't remember. No, it's producing multi of string. So it will be also multi of string. And this will be produced servicer event. No, no. Oh, no, no, this is not producing anything. What am I doing? Oh. So here we have a little more complex pipeline, which we are like calling with transform. There are multiple ways how to do this. Here, for instance, you see that item callback, which in Mutiny is also defined by Fluent APIs. So we are just like processing items, ABC, and filtering them, changing them in multiple ways. What your question is like correctly like finding out between the lines is that this is not particularly easy to basically read from a normal perspective, because you see that basically that individual callbacks are here, they are visible, just in your mind you need to put the whole transformation together from the other side. you are basically doing more a functional way of writing the code, which is not very well, it's not okay to comprehend for everybody because it's just a different way how we are thinking. But for me, typically, I really like to use this example. Imagine that you are ordering coffee in a coffee shop and in Starbucks. Uh, in normal coffee shop, you will basically come to the shop, you will stand in the line for the coffee. When you will reach the counter, you will order your espresso because that's the only correct coffee. And basically, imagine that in blocking way, you will make your order, you will pay money, and you will stand there for the whole duration of the preparation of espresso. Which, when I am preparing on my machine, which is like 1 meter next to me, it takes like around 4 to 5 minutes, like the whole event. So imagine that in blocking API, you are just standing there for 5 minutes, like basically looking at the barista preparing the coffee, and everybody behind you is just standing with you because they cannot move to the counter until you will get your coffee. When you will get your coffee, your result, then you can go and sit and enjoy your espresso. With Mutiny or with reactive programming, it's more like Starbucks. You will come to the counter, you will order espresso, you will get back a ticket or like receipt, which is your promise that you will get coffee, and you will go directly to a table, not blocking the line anymore. When you're so anybody which was behind you can make their order right away. When your coffee is ready, you will get the notification from the barista and you will take your espresso. So you are not blocking the line in between. So basically, the problem is that many people don't really think when they're writing the code in this way. However, you see that the utilization of the resources is way better. The problem, which is really at hand when you are writing this, these examples are rather simple. If I would, should I? Should I discourage you? I think that I have it open here because I was working on Small Eye Health today. So this is my project called Small Eye Health, which is also an extension which we will be checking in chapter 10, I believe. Uh, Here, the main class, because Small Eye Health is fully reactive, this is the main class or main entry point, Small Eye Health Reporter. If I would show you like how this can look like in real world example, yeah, this is good. You need join some bunch of different classes. Uh, do, 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 do. Yeah, here we have again join something, collect everything. This is not that complex after all. So this is not a good example. But I thought that I had more of this. Maybe in here. Yeah, here is the better. So here you can see that this can become very hard to read if you don't know what you are like looking for. Because for instance, here I am already receiving a uni as an argument, and I am just defining more callbacks or more processors on it, passing it back to whoever code is, which is called here or here. And here you can see that I am basically just taking the health check, which is actually passed by a user, and passing it to this vid recovery to actually do some stuff on top of it to handle failures, but it doesn't matter. But you can see that this can become quite complex. So this is one problem that I can see, that many people are finding it hard to read. The other issue, which you will definitely run into, is that if I would try to debug this, and I haven't even tried to call it, so I wonder if I can call it even. Uh-huh. Hello, book. Hello, book. Yeah, so it works. So if I would try to debug it, uh, I don't know if I mentioned that every time that you will start Quarkus in dev mode, let me just try it, run it in dev mode again because I would need to scroll to the beginning. Every time you will run application in dev mode, it will, by default, open a debug port for you here. So it will open a remote debug port on port 5005 by default, but if you have multiple dev modes running on a single machine, then it will find some different free port. So I can directly from my application, if I want to debug, go to plus remote JVM debug. I usually call this just 5005, connects to 5005, and I can directly debug my application. So now I am actually connected to the dev mode. So if I call my application again, I should get my dev mode here. So one thing is that because this is asynchronous result, if I would like to step into any of these callbacks, I actually can. That's strange. Okay, I didn't know that idea is actually doing this because I would say no, you cannot. It's just stepping over it, but you don't really see like any of the intermediate results. You cannot really see what is happening inside the chain until you basically will get out or you will have some like subscriber. So you can step, but you are not like seeing what is happening inside the transformation. If you want to go inside the transformation, I think Uh, yeah, I'm not actually sure. Yeah, now I think that I would be able to get inside. Let me close this. One more. What is happening? Mateus is jumping because he turned on his camera and I don't see what I'm like running the commands for. So let me just restart this because I don't know where did I lose the debug. So I think that if I go inside, yeah, I can go inside, but it's not very like intuitive to see. Like actually, I'm very surprised because I didn't thought that the debugger will stand on every line. So like I'm pleasantly surprised because it's some time that I did it. So probably idea is better now than the last time that I did it. So one thing is really the debugging because you don't really like see what is happening. If I would for instance, try to, oh, this is not doing, turning anything, just here. To new stack trace. If we would check the actual stack trace, where is the stack trace? Yeah, you will see that this is not extremely pleasant. This is just that single stack trace from that exception, which I'm printing in a one of the callbacks. So you see that there is a lot of like processing in the background, like some like multi-classes, multi-on item invoke, vertex recorder, multi-operator processor. There was some subscriber, multi-subscribe. So you see it's not extremely easy to see where you are or like what is actually going on. Somewhere there you should see that you are inside your code. Yeah, so I can see it here that I am in greeting resource on line 32, which I hope it's line 32 here. So you see this is probably the biggest issue that I personally see with reactive programming. If something doesn't do or something in your callback doesn't do what you are expecting it to do, it's quite hard to figure out what exactly is wrong. I hope that answers the question.
Uh, I would like to ask another question about this subject. Uh, how can I be sure that my code is uh, is not blocking something?
Good question. So let's change the exception to actually sleep 5 seconds. So as I was mentioning from the beginning, when you are running asynchronous code, all of these callbacks by default run on event loop. So anytime you will return actually a reactive type, and it doesn't only need to be uni or multi, it also can be like completion stage, I think, or completable future from a Jaxares method, for instance. Quarkus will automatically assume that you are writing asynchronous code in this hello method, so it's safe to run it on event loop. If you, well, actually, let me do it not here. let's park this. Let me actually do it in, let me do a new methods because that will be better for explanation. So I will do blocking string, which will be blocking and returning hello blocking. So if I would now call my hello blocking, after 5 seconds, I shouldn't probably do 5 seconds because this take forever, I will get back the result. So everything is fine because when I'm returning anything else than uni or multi or any reactive type, by default, this will run on a normal blocking platform thread, normal operating system thread. So if we would see out here, thread, current thread, get name, I should actually, and let me do a little bit less because that takes forever. So after 3 seconds, and let me actually do it in the better, we will see this executor thread, which is in Quarkus that worker thread. Let me put this to the beginning. Because I want to have it here. So now if I will do exactly the same method, just reactive, instead of string, I will return uni of string, and this will be reactive blocking, doesn't matter. And I will return uni create from item hello block. What? Hello. Really? Come on, idea. You can do better. Like this, and I'm missing one here. Let me just first do it without. So you will believe that it, oh, not blocking. Active. I will already see that I am running on the event loop thread, so no longer on the thread, and this is just by returning reactive type here. And now to the question, what will happen if I will block the event loop thread? Because now you believe me that I'm actually running on event loop thread. What will happen if I will block the event loop thread? Yeah, very nice exception. My event loop thread has been blocked for 2 seconds. Time limit is 2 seconds, exactly where it was blocked. And you basically see that somewhere, yeah, it's not here anymore. I thought that that exception should be telling you cannot block, but like more or less it's clear from it that you cannot block it for more than 3 seconds. What is funny is that I'm still running reactive. Sorry. This will actually continue. This will return the result, and you will see that this will not always catch it because that scheduling on the event loop or watching for the actual resources is not like starting with every time you will run the code. It's really the time limit is 2 seconds, so not every time you will get this, but you see that you still get back the result. So this is really just a warning. It's not that your application will crash, and you see that this time I was lucky because I catch the like watcher on the event loop thread. It's not like that your application will start functional. It's just an anti-pattern because when you will block the event loop thread, you are putting that whole reactive architecture which we had on that slide somewhere, that whole reactive architecture to places which we shouldn't say on YouTube. Basically, this whole concept relies on you not blocking other like operations that can use the same operating system thread, which in this case is event loop. If one of these will start doing something wrong, this whole architecture goes away. So Quarkus will warn you, and you don't really want to do this because then basically you are going back to an imperative programming, just writing it in more complex way. So hopefully that explains what you are asking.
And if I put the annotation non-blocking,
I will get to that. So, as I mentioned, the default way how we decide on which thread to run is by the return time. If it's anything normal or pojo, then it's running on normal platform thread, which is your executor thread, as you saw, or its name, executor thread. If you return uni, multi, I think also competition stage or completable future, like or publisher, for instance, then by default it will run on event loop thread. However, you can override both of these with either non-blocking annotation or blocking annotation. So now, if I will call my blocking API, we should see that it's running on event loop, and my reactive API will run on executor thread. So you are free to override this on any way you like. However, then you need to know what you are doing, because again, the default assumes something based on the type that you are returning, which is usually the safest bet. If you are using these two annotations, then it's up to you to make sure that you are not actually blocking, because this is actually a blocking call. When you are doing thread sleep, that's like manually telling the operating system, like, idly block the thread for 3 seconds. So if you are doing some operation like this, or you are doing a remote call or database call or something similar like that, and you are running it on event loop, then you don't really or you can't really be sure that it can run on event loop every time, even if it's like 99.99 times like percentile fast enough to run on event loop. It's just okay that your database is down, for instance, and then you are blocked for the whole duration until it will come out, or there is a timeout which usually is longer than the 2 seconds. So uh, it's it's possible. You have these APIs. It's also written in the book, but like, you need to know what you're doing. And with that, because we are running a lot out of time, so I will continue for now, because I still want to do Project Loom, and I will take more questions at the end. I just want to mention.
just just
Go ahead.
to Mussolini said it's like you lost middle of jungle. It's very sensitive. I think that I uh, the Mussolini mic is not okay, and he are typing in the chat. It's like you lost
Yeah,
middle of the jungle. It's very
we
sensitive.
can take it at the end, because then I will like read the chat and we will continue. So here you can like just really quickly see what changes we are actually doing inside the book to adjust everything, or what we already did basically in the book to write reactive code. But I will leave that for you to read. I really just want to really quickly finish in the last 5 minutes with Project Loom, because that's the question that everybody has. And with that, I will go back to the slides. What is this Netty project? I don't know how I open Netty project. So with Project Loom is fully supported in Quarkus since it was in preview in JDK 19, if I remember correctly. However, there is no single global flag that will run all of your application on virtual threads. In Quarkus, you need to manually annotate every method, or you can put this run on virtual thread or annotation also in a class. Every basically CDI method, and this is what I forgot to mention, this all of this blocking and non-blocking and uni, multi-string, etc., works on any CDI bean. So it's not only in JAX-RS resources. This is working for any normal scope like bean which you will define in your application. And this is also true for run on virtual thread. So you just manually need to put this annotation every time that you want to run on virtual thread. So just that you believe me, I will again take my blocking call and I will do loom. Loom. And that's it. All I need to do to run it on virtual thread is this annotation, and then I can do Loom, and we will see that we are running on virtual thread this time. And you will see that every time I am running on a virtual thread, which I, oh, sorry, I called reactive. So I will call Loom again, and you see that every time I'm running on a new virtual thread. And now let me really quickly explain what virtual threads are. So I need to move Mateus again somewhere else because I want to do it in slideshow. So we have exactly the same scenario again, but this time with virtual threads. With virtual threads, Project Loom, you have two types of threads. Virtual threads, which are the threads on which your code is running. However, they are only virtual. They don't really exist. You have this second type of real platform operating system threads, which in Project Loom are called carrier threads, which are really the real thread which is going to execute your code. So when you have a request coming to your application, there is a new virtual thread created because virtual thread is it only exists inside the JDK. It's only a virtual concept. It doesn't really it's like not that operating system knows that this exists. It's just a structure inside the JDK. So it's typically extremely small and extremely fast to create. So it doesn't really make sense to reuse virtual threads. And this is by design by Project Loom. So every time that you are working virtual threads, you typically create virtual threads for every task that you need to execute. And when you are finished, it's directly thrown away. So it's garbage collected. So you will typically run like billions of virtual threads. It doesn't really matter because it's not a real thread. It's just a structure inside the JDK. Because what is the problem with like big normal virtual threads is that you cannot really have them forever because you are limited by the memory, which is quite a lot that they are taking, and also the switches between different threads usually take a few cycles on your CPU. So the more that you need to switch, it's like more problem. But with virtual threads, this problem doesn't exist because they are just memory structures, objects in your JDK. So I will get my request. I will get a new virtual thread one from the JDK, and I will start executing my request. However, this is not really executing my request until there will be a free carrier thread that will start actually executing that virtual thread code. When we are getting the remote request from my like execution of request one, then basically the logic inside the JDK will unmount the virtual thread from the carrier thread, and you are blocking only the virtual processing inside the JDK on the virtual thread. If there is a second request coming in the background, again, we will get a new virtual thread, VT2 in my case. I will start executing virtual thread. Again, I need to mount it on some carrier thread. I don't remember what is the default number out of the box for carrier threads, but let's assume that I have only one, but it's free, so I can start executing virtual thread 2. Again, I will get to the remote request. I will unmount the execution from the carrier thread. I will block only VT2. If there is a response back from the first request, I will notify virtual thread 1 that the response is available, and I will mount it again on the free carrier thread to execute basically the callback, which is, in my case, only normal processing, because as you can see, this is exactly the same as we had with blocking APIs. In my code, where is it? This is exactly the same as my blocking call right here. The only difference is this run on virtual thread annotation. Otherwise, these methods are exactly the same. And actually, two same. I should actually change this. What is it? So and we are continuing like and we are continuing like this. So when we are finished with virtual thread 1 with request 1, as I told you, the VT1 is just destroyed. It's garbage collected. When I will get the response back from request 2, I will again execute the callback. Again, when I'm finished, everything goes to be garbage collected. If I have like the third request, exactly the same thing. But what I want to show you is this, of course, continues, is that if I will put this together, doesn't it like really look like that this top part looks like your imperative programming model, which is exactly what Project Loom promises for you, that you write exactly the same code, but this down part look very closely to event loop processing and your reactive programming. So you see what Project Loom basically did. They hit the complexity of reactive programming inside the JDK with these carrier threads. And from your perspective, you are still writing the same interactive code as you are used to, and it's easy to like debug, read, to work with in general. Just you will get all the performance benefits inside the JDK with these carrier threads, and you don't see it in your code. However, uh, this is like very nice on where is it? Very nice on paper, because like really all changes that I need to do on my application is to put this run on virtual threads on like everything like in my application, right? It's not so easy. Typically, you will run into an issue because these carrier threads are, or like, let's put it this way, event loops are normal platform threads which are fully operated by Quarkus, and Quarkus can decide to run something on virtual thread or not run it on virtual thread on its own. However, that carrier threads API is not exposed out of JDK, so Quarkus cannot touch the execution on carrier threads. And carrier threads will out of the box scale basically its own pool, which is basically I really don't remember on what it is starting, but basically if you have too many virtual threads and they are waiting for too long time to get a free carrier thread, then JDK will actually create new carrier threads, so new operating system threads just to manage this load, and it can also scale down, of course. But the problem with this is that they can scale, and they will scale basically in several cases, uh, which I want to just really quickly touch on, and we will finish with that. So if you are basically, yeah, I already told you that. You can actually watch for that if you want to. You can check that later. I will send you the slides, so they will be available in the description on YouTube. Uh, it can with virtual threads you can have this pinning, which is basically in very short, when you block the virtual thread, it also blocks the carrier thread. This used to happen in two cases when you had basically a synchronized block and you did your blocking operation inside the synchronized block. This was fixed already in JDK 24, and it's now fixed in JDK 25 fully. So this no longer calls is pinning. However, the second case, if you have a native call in your stack, will still pin the carrier thread. And this is not usually something which you see, because it's usually handled by the library or Quarkus in our case. And I believe that we have 13 native libraries in Quarkus. So if you are lucky enough to actually work with something which is touching a native code, then you cannot basically unmount the blocking operation from the carrier thread. And you remember what I told you, that if this looks like event loop, you should never block event loop thread. And this is also the true for virtual threads. You should never block carrier thread. But because you are not controlling it, we cannot even tell you that you are blocking the carrier thread because we don't see it from Quarkus. Yeah, so that would be pinning. The other problem, which is also true for reactive programming, is just monopolization. If you are doing any heavy computation on event loop thread, it takes more than 2 seconds, you will be warned this is not the thread which is intended for this long computation. If you are doing very heavy, long computation in virtual thread, you will just occupy the carrier thread until it is finished. So if you are not causing any blocking, which are actually defined operations inside the JDK, which will unmount your virtual thread from the carrier thread, then you will just basically use the carrier thread as any normal virtual thread. And there is also, it's basically just like going into detail. The problem with thread locals and object sharing, because I'm not sure like how much you are using thread locals in your applications, but thread locals are heavily used in like things like REST, for instance, because we typically need very big objects to basically do some parsing or something like this. And because we usually had like 20 operating system threads in a pool, which we reused for different HTTP requests, it actually made sense to cache these very big like objects like parsers in thread locals on each of these threads because they were actually reused. However, Project Loom fully supports thread local APIs, but it copies each thread local to every virtual thread. So you can run actually out of memory because you are just copying these extremely big objects all over the place. Uh, yeah, and I think that I can skip this. So, more or less, that would be everything. It's also written in here in a little bit, like probably a little bit more detail. But this is everything basically that I wanted to show you today because, like, Project Loom has its place. However, I really think that it's kind of like putting your cards into somebody else's hands because you are not in control. You are letting the JDK decide when it's a good idea to unmount your execution from carrier thread. With reactive APIs, you can write, sorry, your pipeline in a way, and we actually have it in the book, but it will be in the next chapter, that when you want to execute some blocking operation, I can just call a different method in my pipeline somewhere here, just called like invoke and call some method, which will be annotated with a blocking annotation. And it will basically run only that part of the pipeline on a worker thread, on that executor thread. And then when that part is finished, it will return all of the other processors back to the event loop. So you are really in full control and you can get the best performance out of your application because you know what needs to be run as a blocking, and everything else can use the full potential of the resources that you have at hand. And with that, I will end my talking today. So, any questions? Anything to add?
From my side, I think no. Marceline, do you have any question? No. Okay, great.
I'm just reading the chat, but like if you got everything, then we can finish.
Okay, and just to ask the next chapter, what is the topic of the next chapter?
So the next chapter will actually take this what we just learned today, and I will show you what Quarkus messaging is, which is basically originally it was called reactive messaging. So you see like where we are going because the Quarkus messaging actually doesn't require you to write reactive code, but the whole messaging processing is written through these reactive pipelines. So we will actually learn how to use Kafka and RabbitMQ that we are using for communication between some services, which I forgot which ones exactly, but we are using it heavily in the book.
Yeah, yeah. Okay, thanks a lot again, Martin and Mussolini. We had today some people, new people, but unfortunately, uh, it was not possible to present uh, them. But okay, uh, okay. The link to the presentation will be in the description on YouTube description. And see you in the next chapter. And bye bye.
Bye.